Ordinary differential equations, or ODEs, are used in engineering and science to describe how an unknown function depends on its derivatives. An example of an ODE that you may have already seen is Newton's law, which describes how the acceleration of an object, that is, the second derivative of position with respect to time, depends on the forces acting on that object. Now, ordinary differential equations is a very important topic in engineering. In fact, we'll spend most of the rest of this course looking at more and more sophisticated tools that we can use to solve ODEs. Now, when we're dealing with an ODE, it's a bit like we're dealing with an integral. The method of solution is going to depend on the type of equation that we're dealing with. And the solution itself will be a function, not a number, and it'll involve some constants that we need to fix with additional information, for example, initial conditions. Finally, we're always going to be on the lookout for any shortcuts or tricks that we can use so we can avoid actually doing the integral. Now, in this first lecture, we're going to look at two methods for solving first-order differential equations, which you've probably seen before, the method of separation of variables and the integrating factor method. Now, it's very important to be able to classify what kind of ordinary differential equation you're dealing with, because the type of equation determines the method of solution. So we're going to first of all have to learn how to classify ordinary differential equations depending on their order and depending on whether they're linear or not. So the order of a differential equation is given by the highest derivative. So if I have a first derivative, as in example 1 here, then the highest derivative is first order, and this is a first order equation. Likewise, I've got a first order derivative here, dy dx, so this is a first order equation. But in example 3, y double prime plus 6y prime minus 5y, well, the highest derivative there is second order, and so this is a second order equation. Likewise, in example 4, I've got a second derivative, x double dot, that's often used as a symbol for derivative with respect to time. X double dot, that's a second order derivative, so this is a second order differential equation. So 1 and 2 here are first order. And 3 and 4 are second order. The other important thing to remember about classifying ordinary differential equations is determining whether they're linear or not. Now, what I mean by that is, does the unknown function that you're trying to calculate appear on its own, or does it appear in the form of a function, a multiple, a quotient, or some more complicated expression like that? So we need to identify what the unknown function is and then try and figure out whether or not it's linear in that function. So let's take a look at the first example. dy dx plus y is equal to x cubed. You can see here this is an equation involving the derivative of y, and it involves y, and it also involves the variable that y depends on, but this is clearly an equation for y of x. The next thing we need to do is figure out whether or not this equation is linear in that unknown function. So does this have anything like a y squared or a dy dx times a y or sine of y? Well, no, it's only got dy dx on its own and it's got y on its own. So this is a linear equation. Let's contrast that with example 2. Again, you can see this is of the form dy dx is equal to some function x squared times y cubed. So the unknown function here is again y of x. But you can see that, okay, dy dx appears on its own. But on the right-hand side, I've got a y cubed. So that's a y times a y. This is not a linear function. This is non-linear. Let's look at example 3. This time I've got a second order differential equation, so it's got a second derivative of y, a first derivative of y, and y on its own. Now we're not actually told what the dependent variable is here, let's just call it x. So the unknown function is y of x again. And the question we need to ask is this a linear equation or a nonlinear equation? Well, again, the question we want to ask is y on its own, and is each derivative on its own? Yes, it is. So we've got y on its own here, y prime on its own, y double prime on its own. I don't have any cross terms like y times y double prime, and I don't have any products like y squared. So this is a linear equation again. Last example, example 4, we saw that was another second order equation. The first thing we need to determine is what is the dependent variable and what is the unknown function. You can see here I've got derivatives of x with respect to time. So this is a function x of t. So x is the unknown function, t is the variable it depends on. And once again, you notice that you've got a complicated dependence on t on the right-hand side, but that doesn't matter because we're only interested in whether x is linear. So x appears on its own here, the derivative of x appears on its own, and the second derivative of x appears on its own. So this is also a linear equation. So once we've figured out what type of equation we're dealing with, then we can start to look at different methods of solution. Now, there's a couple of things to bear in mind when you're looking for solutions of ordinary differential equations. The first is that you'll often, and always in fact, get unknown constants. Those constants are basically constants of integration in exactly the same way that you get constants when you do integrals. Essentially, finding the solution to an ordinary differential equation is equivalent to doing an integration. And it's very important to treat those constants with some respect because they've got to tell us some extra information. We're going to need some additional information to fix them, for example, some initial conditions. Now, the number of constants that we'll get should always be the same as the order of the ordinary differential equation. It's one of the reasons that we want to be able to figure out what the order is. And the reason for that is because the order of the ordinary differential equation is the same as the highest number of derivatives. And each time we do an integral to get rid of one of those derivatives, we introduce a new integration constant. So the order is the number of derivatives we need to get rid of. In other words, the number of integrals we need to do. In other words, the number of integration constants that we get. And we're going to fix those integration constants using any initial information that we're given. So again, we're going to focus in this lecture on some first order ODEs and methods for solving them. Some of these you've probably seen before, but otherwise it's good revision. And then in the next couple of lectures, we'll look at second order differential equations. The first method that we're going to look at is the method of separation of variables. So this is for a special class of ordinary differential equations, which are called separable differential equations. Now, a separable differential equation is basically one that I can rewrite so that all of the variables of one kind are on one side of my equation and all of the variables of another kind are on the other side of the equation. So basically we're separating the y's to one side and the x's to the other side, or whatever. So let's take a look at how we might solve a problem using the method of separation of variables. So we've got dy dx is equal to y times 2x plus 3. We see that this is a first order differential equation and it's linear in the unknown function y of x. The other thing is that we're not given any initial information here, so we're going to end up with an unknown constant that we're just going to have to keep in the solution. So the way that we're going to solve this is by taking that dy dx on the left hand side and pretending that it's actually a fraction, dy divided by dx, and then I can multiply up by dx to bring the dx to the right hand side. So again, what I did there was I pretended that dy dx was actually a fraction. I took the dx from the bottom and multiplied up on the right hand side. You notice that I've got a factor of y on the right hand side, so let's get rid of that by dividing it over to the left-hand side. So that's going to give me an equation now in which every term involving y is on the left and every term involving x is on the right. So we've essentially separated this problem into a y problem and an x problem. And we're going to solve those separately by integrating each side. You see, I've transformed it now into two sets of integrals. So the first integral, the integral of dy with respect to y, is straightforward to do. That's going to be the natural logarithm of y. The right-hand side is also straightforward to do. I'm going to have 2x squared over 2 plus 3x. And I need to include a constant of integration. Now you notice that I've only included one constant of integration because even though I had two integrals to do. And the reason I did that was because even if I added a constant of integration on the left-hand side and the right-hand side, I could basically combine them into a single unknown constant. After all, that constant hasn't been fixed yet, so it could contain both constants of integration. So when I do the separation of variables and I do my integrals, I only need to have one constant of integration at this point. Now, we're not quite finished yet because I'd like to find a solution for y of x. So let's try and rearrange this equation to do that. I'm going to take the exponential of each side of this equation, so e to the natural logarithm of y. That, of course, is simply y. E and natural logarithm cancel each other out. And let's take the exponential of the right-hand side. You notice I can cancel out some factors of 2 there. So taking that out, exponential of the right-hand side gives me e to the x squared plus 3x plus c. Now, using the laws of exponentials, or powers, I can write that as a product, e to the x squared plus 3x times e to the c. And if I introduce a new unknown constant, a equals e to the c, I can write this whole solution as y of x is equal to a times e to the x squared plus 3 of x. So here's my solution, and you notice that the constant of integration is actually appearing in the form of a multiplicative constant, a multiplied by e to the x squared plus 3x. And that can happen, and indeed it happens quite often, that I get a multiplicative constant of integration, not an additive constant. And that's basically because there's some sort of hidden exponential that's happened. So let's take a look at another example of the method of separation of variables, this time where we've got some initial information that we're going to use at the end of the problem to fix that unknown constant of integration. So once again, I'm given a first order differential equation. dy dx is equal to cosine x over y. This is actually not a linear equation. This is a nonlinear equation because you notice that y appears on the right-hand side in the form of a function 1 over y, and 1 over y is not a linear function. So this is a nonlinear first-order differential equation, but we can still use the method of separation of variables by splitting up that dy dx into two pieces, dy and dx, bringing all the y's to one side and bringing all the x's to the other side. So dy dx, I can take the dx on the bottom, multiply it up, take that y on the bottom there and multiply it up on this side to end up with y's on the left and x's on the right. Now I've got something I can integrate both sides of to get an equation for y squared over 2 is equal to the integral of cosine of x, which is sine of x. And once again, I've got a single unknown constant of integration that I need to fix. Of course, I've done two integrations, but I did them at the same time, so I can combine their two constants of integration into a single constant c. Now we need to fix c, so what we're going to do is make use of that initial condition. That is that when x is equal to pi over 2, y is equal to 5. So let's put that in. Let's set x is equal to pi over 2 and y is equal to 5. So I'm going to get 5 squared over 2 is equal to the sine of pi over 2 plus c. This is a single equation now for c, so I get 25 over 2 is equal to 1 plus c, which gives me that c is equal to 25 over 2 minus 1, which is equal to 23 over 2. So putting that all together now, we've got the equation y squared over 2 is equal to sine of x plus 23 over 2. So if we rewrite this as a single equation for y squared of x, this is equal to 2 sine x plus 23. And you notice that I didn't bother trying to write that as y of x, because then that would then have to be an explicit equation for y of x. So I'd have to have a plus or a minus. This is as far as I can go, and this is an implicit equation for y of x, not an explicit equation. So I don't want to have to write that as two separate solutions, plus or minus. So that's a method that we can use to quite quickly solve equations that are of the separable form. That is, an equation where I can drag all of the parts that involve y over to the left-hand side, all of the parts that involve x over to the right-hand side, and then do the integral then solve the problem by essentially doing two integrals. Now, most linear differential equations are not solvable like that, so we're going to have to look at a more general method. That's the method of integrating factors. So these are equations that are of this form. They're linear ordinary differential equations. So you can see they're also first order, so dy dx is the highest derivative. And they depend upon y, but only in the form y or dy dx. Now they can have a complicated dependence on x, however, the dependent variable. In fact, I could have an I could have a complicated function p of x and a complicated function q of x appearing here on the right-hand side. So the method of solution here is basically to use something called an integrating factor, which is given by this expression here. R of x is equal to e to the integral p of x dx. And then the solution is given by this expression here. So first of all, I'm going to prove that this is true, and then I'm going to take you through the steps we need to use this method, this integrating factor method, to solve first order general ordinary differential equations. So to see where this expression comes from, let's take a look at the following derivative. I'm going to take the derivative with respect to x of this product, y of x times r of x, where r of x is e to the integral p of x dx. So y of x is our unknown function of x, but it's still a function of x, which means I can take its derivative with respect to x. You notice here I've got the product of two functions, so I'm going to have to use the product rule. So I've got dy dx multiplied by r of x plus y times dr dx. Now let's think about what dr dx might be. Remember, r of x is equal to the exponential, let's write it like this, exp of the integral of p of x dx. How do I take the derivative of that? Well, you see I've got an exponential of a function of x, so I'm going to have to use the chain rule. So dr dx is going to be equals to the integral of the derivative of the integral. So using the fundamental theorem of calculus, that's just going to give me p of x multiplied by the derivative of the exponential with respect to its argument. So that's just the same thing again. But you notice that I've got p of x times the exponential of the integral, which is simply r of x. So this is px r of x. So what that tells me now is that the derivative of r with respect to x is p times r. Let's put that into our derivative up above. So I've got d dx of y times r is dy dx multiplied by r plus y times p times r. And you notice there that I've got a common factor of r. Let's take that out. Which leaves me with dy dx plus p of x times y. But that term in brackets there looks very familiar. In fact, it's exactly the left-hand side of my original differential equation. It's exactly this term here on the left, which means that that whole term there in brackets is simply equals to q of x. So what have I found? I've found that d dx of y times r is equal to r of x times q of x. Now I have an equation that I can integrate to give me y of x times r of x is equal to the integral of r times q, and if I divide by r, I get the solution for y of x. Which is exactly the expression that we gave in the formula. Now, just knowing this formula is not enough to be able to solve any old linear differential equation. There's a couple of steps that we want to go through carefully. So let's take a look at an example. Here's my equation that I'm going to try and solve, example 4. dy dx plus 2 over xy is equal to 4x. First of all, we recognize that this is in fact a first order differential equation. The highest order derivative is the first order derivative, dy dx. And it is linear, so it's only got dy dx and it's got y. In fact, I can read off what p of x is and what q of x is. So the first step in solving these equations is going to be to calculate what the integral of p of x dx is. So we know what p is. It's given by 2 over x. So the integral of 2 over x with respect to x is going to give me 2 times the natural logarithm of x. Or if I use the laws of logs, that's the natural logarithm of x squared. So I've just used the fact that a log b is log b to the power of a. Now you notice there that I did not include a constant of integration. We're actually going to come back and try this problem again by including that constant of integration, but what we're going to see is that that constant of integration actually doesn't give us anything new. It cancels out. So I can leave it out at this point without suffering any consequences. Again, I'm going to show you that in just a moment. In the meantime, once I've calculated the integral of px dx, I can form the variable, the function r of x, which is the exponential of the integral of p of x dx. So let's put in the integral we've just found. So we've got e to the natural logarithm of x squared. We've already seen that e and natural log cancel each other out, so I get x squared. Once I've found r of x, now I can calculate that what the integral of q of x r of x is. And this time I am going to have to include the constant of integration. So let's do that integral. What's q of x? It was 4 times x. We've just found that r of x is x squared. So this whole thing is equal to the integral of 4x cubed, which is 4x to the power of 4 over 4, and I am going to include a constant of integration, c. We get cancellation of those factors of 4, so we find that this integral is equal to x to the power of 4 plus c. Final step is to put it all together in our solution. So we've got y of x is equal to 1 over r of x, integral of q of x, r of x dx. So r of x we found was x squared. We've just done the integral of q of x, r of x. We found that that was x to the power of 4. And notice that I'm being very careful with my constant of integration here. It also is being multiplied by that factor of 1 over r. So the solution here is going to be x to the 4th over x squared, so that's x squared, plus c over x squared. So you notice that that constant of integration, c, is actually involved in some function of x here. Now, I pointed out that we didn't need to include a constant of integration here when we were calculating the integral of p. But I did need to include it here. So let's just prove that adding a constant of integration in the p integral doesn't actually give us anything, and so we're free to leave it out. So I'm going to put it in green here just to show what happens, but again remember that we're not going to include it when we do these calculations. So let's include a constant of integration, it's adding in there. So I would end up with a plus a here. And when I do my calculation for r of x, I'd have a plus a here. Now remember, we actually saw in one of the earlier examples that having something like e to the natural log x squared plus a can be written as a product. So that could be e to the natural log x squared times e to the a. So if I call e to the a new variable b, you see I've got a multiplicative constant b times x squared. Let's continue that on through in this calculation. So I've got the integral of q of x r, so that's going to give me a factor of b here, which I can pull outside, and would give me an overall factor of b here. That would give me an overall factor b here as well. Now let's see what happens to my final answer. So I've got 1 over r of x, so I have to include a factor of b there, and I've got the integral, which has another factor of b. So I've got a factor of b on the bottom, and I've got a factor of b on the top, and those two factors exactly cancel out. And that will always happen. Whenever I include a constant in the integration factor, this integral of p of x dx, that constant is going to cancel on top and bottom in my final answer, so that I only have one constant of integration. So I don't need to include that constant in my calculation. On the other hand, the constant that does appear, this c and this constant c, is important in the final answer, so I do need to include that. So let's look at another example. Again, I'm going to leave out the constant of integration when I do the integral of p, but I'm going to keep it in when I do the integral of q. So this is the problem we're dealing with here. The dy dx is equal to xy plus 2 over 1 minus x squared, and we're given some initial information that we'll hold on to and use at the end of the problem to fix the unknown constant. Now the first thing we need to do is to rewrite this so it looks a bit more like what we're used to. So let's separate out that term that depends upon y on the left-hand side. Bring it over to the left-hand side. so that I have dy dx plus a function of x times y is equal to a function of x. So you can see now I can just read off what p is, and I can read off what q is. So once I have p of x, I can calculate its integral. So step by step here, integral of p of x. So that's the integral of, let's not forget that minus sign, minus x, 1 minus x squared dx. This is an integral I can do using an integrating factor. So let's use u is equal to 1 minus x squared, which gives me du is equal to minus 2x dx. So this integral then becomes a half times the integral of du over u. So I get a half natural logarithm of u, or putting back in u again, I get 1/2 natural logarithm of 1 minus x squared. And in fact, I can even simplify this a little bit better. I can take that factor of a half and turn it into a square root. You notice here that I didn't include a constant of integration when I did this integral over u, because again, I'm not going to include the constant of integration when it appears in the integral for p of x. Let's take a look at the next step. That's calculating the integrating factor r of x. So that's given by e to the integral of p of x dx. And you can see now why I was keen to put that factor of a half inside the natural logarithm and turn it into a power, because now I've got e to the log of something, which just gives me, those two things cancel out, and I'm given by 1 minus x squared to the power of a half. So that's my integrating factor. Now I'm ready to calculate what the integral of qx times rx is. Qx, if we just look back up again, was given by 2 over 1 minus x squared. And we found that the integrating factor was 1 minus x to the power of a half. So you see that actually we get a little bit of cancellation on top and bottom there. I'm going to get integral of 2 over 1 minus x squared to the power of a half. It's actually one of the tabled integrals, so that integral is 2 times the inverse sine or arc sine of x, and I need to include a constant of integration. So this is where I do need to include a constant. The final step then is to put it all together. So I've got y of x is equal to 1 over r of x times the integral of q of x r of x dx, which gives us 1 over the square root of 1 minus x squared, or 1 minus x squared to the half. The integral of q times r was 2 sine inverse x plus c. Now we still need to figure out what c is, and we're going to do that by using the initial conditions. So that's our last step here, using the additional piece of information that we're told when x is equal to 0, y is equal to 1, to fix or to figure out what the value of c is. So putting in x is equal to 0 and y is equal to 1 into this expression that we found, we get 1 is equal to 1 over 1 minus 0 squared. That's all to the power of a half, or the square root. 2 sine inverse of 0 plus c. Now sine of 0 is 0, so sine inverse of 0 is also 0. So we get 1 over the square root of 1 is 1. 2 times 0 plus c. So this is all equals to c. So it actually gives me that c is equal to 1. And I find my solution y of x is equal to 2 sine inverse x plus 1 all over the square root of 1 plus x squared. So that's the method of the integrating factor applied to first order linear differential equations. Now sometimes we'll be faced with an equation that doesn't look like it falls into one of the categories that we've seen so far. And we're going to have to use a substitution to transform it into something we can deal with. Here's an example of one of those, example 6. We're given x squared dy dx is equal to x squared plus y squared plus xy. And we're told to make a substitution, v is equal to y over x. So let's first of all take a look at this equation. We notice that it's a first order equation, dy dx is the highest order derivative, but it has a term y squared on the right, so this is a non-linear equation. It's also not an equation that we can write in the form of something involving y on the left and something involving x on the right hand side. In other words, it's not separable and it's not linear, so we can't use either of the methods that we've seen so far. However, when we make the substitution, hopefully we will be able to solve this. So when we're making a substitution, the first thing we need to do is to rewrite this as an equation for y of x. So we've got y is equal to x times v of x. Now notice here that the substitution was given as y, which is a function of x, over x. So that means that v itself is also a function of x. So that's why I wrote here, when I multiplied up by that factor of x, that y of x is equal to x times v of x. So now I can calculate the derivative of y using the product rule. So this is the derivative with respect to x of x times v of x. So this is a product rule. I've got a function of x multiplied by a function of x. So that's going to be given by the derivative of x with respect to x times v plus x times the derivative of v with respect to x, which is simply going to be 1 times v plus x dv dx. Okay, I found y as a function of x and v, and I found dy dx as a function of x, v, and dv dx. I can substitute those now in to eliminate y from my equation and express it all in terms of v. So we're going to eliminate y and dy dx. So substituting that into that differential equation up here on top, I'm going to have x squared times dy dx. We saw that was v plus x dv dx is equal to x squared plus y squared, so y was x times v of x, plus x times v, so that's x times v. Let's multiply all this out, so I get x squared v plus x cubed dv dx equals to x squared plus x squared v squared plus x squared v. And you notice that I get an x squared v on each side, so those cancel out. And I get a common factor of x squared on the left hand side, so I can also take that factor out. So I've got x cubed dv dx is equal to x squared times 1 plus v squared. I can cancel some factors of x squared, so if I get rid of x squared there and get rid of x cubed and replace it by x, I'm left with the following equation: x times dv dx is equal to 1 plus v squared. Now again, this is a first order equation. It's still nonlinear in v, which is our new variable, but this is an equation that is separable. It's one that I can write with v's on the left hand side and x's on the right hand side. So this is a separable equation. Once I've got the v's on the left and the x's on the right, I've got them on their own, I can integrate them. So doing that integral of 1 over 1 plus v squared is the inverse tan, another one of the tabled integrals. That's equal to natural logarithm of x, and I need to include a constant of integration. So I find from this that v is equal to the tan of natural logarithm of x plus c. Now we're not done yet because we need to express this as a solution for y of x, our original variable. So let's sub back in y. So we'll remember that y of x was equal to x times v of x. So my solution is x times inverse tan of log x plus c. And to fix that last variable there, that c, I would need to have some additional information. Let's look at another example where we need to make a substitution. We have x plus y times dy dx equals e to the 3x minus x minus y. So this is a nonlinear problem because I've got a y dy dx, and it's a first order problem. You notice also that we're given some initial conditions that we're going to use to figure out the unknown constant of integration. Now we're given the substitution to make. In general, we'll be given the appropriate substitution in these kinds of problems. And we know that the first thing to do is to rewrite that substitution as y in terms of v and x. So just take the x over to the left-hand side, get an equation for y, and then I can use that to find out what dy dx is. dy dx is dv dx minus the derivative of x with respect to x is 1. So now we're going to use that to eliminate y and dy dx from my ordinary differential equation. So I've got x plus, we saw that y was v minus x. dy dx we saw was dv dx minus 1. On the right hand side we've got e to the 3x minus x, and we saw that y was v minus x. You can see we've got some cancellations here. The x and the minus x there will cancel. And I actually have a minus x and a minus times minus, which is going to give me a plus, so those two will cancel. So that's going to give me now v dv dx minus v is equal to e to the 3x minus v. And we get another cancellation. The two v's cancel out. So I have the following equation to solve. v dv dx is equal to e to the 3x. Again, this is a separable differential equation. I can rewrite this as all v's on the left, all x's on the right, and do the integral on both sides. So the integral of v is simply v squared over 2. Integral of e to the 3x brings a 3 down onto the bottom, and we have a constant of integration c. Remember, I'm looking for the solution for y, so the last step here is to sub in y of x, which we saw was equal to v minus x. So in fact, it's actually easier in this case to use the fact that v is equal to x plus y, because we've got an implicit equation here for v. I don't want to take the square root because that'll give me two solutions. I want to keep this in the form of one solution. So if I do that, I'm going to get v is equal to x plus y, that's all squared, over 2 is equal to e to the 3x over 3 plus c. Now I still need to fix the constant c, so I'm going to do that using the additional piece of information that when x is equal to 0, y is equal to 2. So let's use that. So putting that in gives me x is equal to 0, y is equal to 2, all squared, over 2 is equal to e to the 3 times 0 over 3 plus c. So we've got 2 squared over 2, which is simply 2. Equals e to the 0. Well, e to the 0 is always 1 over 3 plus c. That gives us that c is equal to 2 minus a third, which is 6/3 minus 1/3 is 5/3. So we find that x plus y all squared over 2 is equal to e to the 3x over 3 plus 5/3. And again, you notice there that I have not tried to express this as a single solution for y or an explicit solution for y, because then that would involve taking the square root, which would give me pluses or minuses. I'd have to write that as two different solutions for two different ranges of values of x. Now, in our last example, we're going to take a look at a problem where we're not actually given the ordinary differential equation, but we have to build it ourselves from the information that we're given. Now, the thing to remember is that ordinary differential equations basically relate things that are changing. So we need to figure out what things are changing and how they're related. So in this problem, we're told that we have a room which has got 50 cubic meters of air in it. We've got someone who's lit a cigarette and is smoking away at a constant rate of 2 milligrams per minute. So they're adding smoke to the air at 2 milligrams per minute. So we have a 50 cubic meter room. We're adding at a rate of 2 milligrams per minute smoke. And we also have an air conditioner running that's taking out whatever air and smoke mixture we have at a rate of 5 cubic meters per minute. So we need to figure out what is the relationship relating the amount of smoke in the room in milligrams and time. So the way that we can do this is by writing it out in terms of English, right? So the rate of change of smoke in the room is going to be given by the amount of smoke added per minute minus the amount of smoke removed per minute. So the rate of change of smoke is smoke in minus smoke out per time. Now smoke added per minute, that's fairly straightforward. Chris is sitting at the back of the room smoking away and adding 2 milligrams per minute every 2 milligrams every minute. But how much smoke is being removed every minute? Well, it's not a constant amount. In fact, it's going to be determined by how much smoke is in the air, right? Because we're constantly removing a certain amount of air and cleaning it, so the amount of smoke removed depends on how much smoke is in the air. So we're going to write the amount of smoke removed per minute is given by the amount of smoke per volume multiplied by volume cleaned per minute. So you can notice there that I've almost like multiplied and divided by volume. Smoke per minute is smoke divided by volume, volume per minute. So what is the smoke per volume? Well, that's going to be the total amount of smoke, which is an unknown value S, per volume is 50 cubic meters. By volume cleaned per minute, well, that was given by 5 cubic meters per minute. So now I have a single equation for ds dt. So I've got 2 minus, I can cancel two factors of 5 on top and bottom, s of t divided by 10. So that's my equation. Let me write it out again. ds dt is equal to 2 minus s of t divided by 10. That's my linear ordinary differential equation, and it's first order. We're going to solve this equation now using the method of separation of variables. So let's take out a common factor of 10. So 1 over 10 times 20 minus s of t. Let's take the factors of s over to the left and the factors of t over to the right. So now I've got s's on the left and t's on the right. I can integrate both sides. The integral of the left-hand side can be done using a substitution, or you can just read it off. It's going to be given by minus the natural logarithm of 2 minus s. And the right-hand side is going to be given by t over 10. And of course we need to include a constant of integration. Let's now solve that for s of t. So taking an exponential of both sides. In fact, if I deal with that minus sign first, it might make life a little bit easier. So let's take that as the natural logarithm of 20 minus s equals minus t over 10 minus c. Then take the exponential. So e to the log 20 minus s is equal to e to the minus t over 10 minus c. Exponential and natural log are inverses of each other, so that's going to give me 20 minus s of t on the left-hand side is equal to e to the minus 10t, and I can introduce a variable a, which is e to the minus c. So that additive constant of integration is turned into a multiplicative constant because I've got exponentials. The last step then is just to rearrange this to find a solution for s of t. So I've got s of t is equal to 20 minus a e to the minus t over 10. Now we still have that unknown constant of integration, a. We're going to fix that using the initial condition, which is simply that there's no smoke in the air at the beginning. So s, when t is equal to 0, is simply 0 milligrams. So let's put that in. When t is equal to 0 here, I get s is equal to 0. So that's equal to 20 minus e to the 0 times a. E to the 0 is 1. So that gives me a is equal to 20. And so I find that s of t is equal to 20 minus 20 e to the minus t divided by 10. Now the last part of this problem asks you to calculate how much smoke is in the room after 4 minutes, and that's straightforward to do now that we have our equation here for s of t. So you can just put that into your calculator, but when t is equal to 4 minutes, we get that there is 6.6 milligrams of smoke left in the room. So sometimes we have to set up ordinary differential equations ourselves, and to do that we need to be able to relate how a function is changing to the function itself, and sometimes it's not immediately obvious how to do that. We have to work through sort of using a bit of common sense and some problem solving.